Welcome everybody. Thank you for joining us for another fantastic webinar. This one's been put together by Rick Valenta, inviting a series of experts from different deposits, giving their perspectives on their favourite rocks from around the Northwest Minerals Province. Before I hand over to Rick, I just wanted to give a shout for next week's webinar, which will be on the New Discovery Program, which is the Geological Survey of Queensland's funding program to boost discovery and exploration in the Northwest Minerals Province. This is wrapping up into coming up to its final year of what do we call it, being carried out in the next year. And so a lot of the data that we'll be presenting next week will be, the sort of coming up to the pointy end of all of those projects. And we'll hear from GSQ geologists as well as all of our collaborators under that program, which will of course be the University of Queensland. Codes will be represented there from the University of Tasmania. We'll have CSIRO, we'll have JCU up in Townsville, and I'm sure I've forgotten some, but a great cast of people. It'll be a slightly longer session with 20-minute talks from each of our speakers, starting at 1:30 and going through till 4:30. And the detailed time schedule for that program should be available on the registration page, so that you can jump in and out of the talks that might interest you, just like a normal conference. But for now, I will hand over to Rick. Don't forget, we've got drinks after this, so stick around if you want to have a digital web networking session, and we'll see you all then.
Great. All right. Well, thanks very much, Helen. And before we get going, I just wanted to pay our respects to the traditional owners of the lands that we're holding this webinar on, and their leaders past, present, and emerging. This is a slightly different webinar to the previous ones. It's like a show and tell of some of our favorite rocks, and I'm hoping that because we're only covering 6 deposits, I'm hoping that that we'll get the chance maybe sometime down the track to do this more. And then the other thing that I wanted to do was often in these sorts of talks, if it's a 15 or 20-minute talk, 85% of the talk is showing maps and diagrams, and occasionally people look at a rock and they rarely really spend a lot of time on it. So the whole aim of this one was for people to show their favorite rocks from some important deposits and say what they can see in them. So that's what I'm gonna try to do here. So I'm gonna start by talking about the George Fisher deposit, which is sitting here about 20 kilometers to the north of Mount Isa. And this is just a picture taken from our geoscience analyst compilation for the George Fisher deposit. This diagram is as well, but it's taken from Pete Forrestal's paper in the AusIMM, showing a cross section with the ore bodies dipping to the west. So there's 3 ore bodies in the hanging wall, a bunch in the footwall. And the area that I'm focusing in on here is one ore body. It's an area where the ore bodies are folded and thickened. This is a pyritic layer in here. The rest of this is more lead zinc rich mineralization with polyclinal disharmonic folding. And the rocks the rock that I'm going to be looking at is sitting in and around this fold. I'm saying that because when I actually show the rock, it's going to be on its side so that it fits better in the picture. So this is my favorite rock. There's the 2-centimeter scale. This was collected over 30 years ago now when I was doing my PhD at George Fisher, and it's a rock that's not untypical of the lead rich and copper rich part of the ore body, which is in the hanging wall at the down dip end of the mineralization. And what we can see obviously in this rock is that there's a very nice fold in the stratigraphy of the Urquhart Shale, and you can see these darker layers are more the calcareous mudstones of the Urquhart Shale, and then these more brown, darker brown and lighter brown layers are the pyritic layers. You can see a whole series of veins in here, these whiter and sort of more gray veins. Some of you might have picked up already that one limb doesn't have very many veins, and the other limb has a lot of veins. And and then the other thing is that you can see these layer parallel veins. This part of the ore body is quite full of these veins that, you know, you might think were, you know, you might sort of dispute what their timing is, but what we can see here clearly is that these veins are forming, in this case, as saddle reefs associated with this folding. And what you can also see in this diagram is that there's sulfides in here. So this is a mixture of pyrrhotite and some galena that's then overprinting, you know, eating into these layer parallel veins. And what you can also see, which is very nice in this rock, is a zone of brecciation, which is really quite common in the lead and copper rich parts of the ore body. So you may even be able to see there's some really fine layering that's folded into, you know, crazy polyclinal disharmonic folds in through here, a lot of pyrrhotite, chalcopyrite and galena, and you can see that, again, you know, folded stratigraphy in here. So have had this rock sitting on my back deck for the last 30 years. And when I collected this rock, I had no idea whatsoever about the sort of things that you can do these days with XRF scanning. So this is actually an XRF scan, and thanks very much to Anthony van der Ent from the Center for Mineland Rehabilitation who did this scan. We've got a couple from here. What we're looking at here is iron, manganese, and calcium. So iron in the red channel, manganese in the green, calcium in the blue. And so what you can see here is that these zones in here are quite calcium rich, but they're also, because they're quite light colored in general, they're also quite rich in manganese and iron. So these are, and you've got a similar sort of composition looking carbonate in through here. So these are iron, manganese, calcium carbonates, anchorites, which are really common in George Fisher. And you can see again this saddle reef forming in the hinge of the vein. The really strongly red material here is the pyrite. And I'm not going to show all of these. We might come back to them because I can see that I don't want to be the first person, make a bad example and run everyone out of time. So what I'm showing here now is that I've taken that same iron, manganese, calcium diagram, but then done a level slice to highlight in this light green sphalerite, in blue galena, and in this sort of more orangey color chalcopyrite. And you know, when you look at sphalerite, which is shown in green in here, you can look at that and say, oh well, the sphalerite's quite bedded. It's cut by these veins. You can actually see seams of the sphalerite that are moving in through here that appear to be parting. And there's another zone of sphalerite in through here. And here's another bed of sphalerite. Let's follow it around the fold hinge. Oops, the sphalerite's gone. And this is a really common thing that you see in this area, and I think in these deposits in general, that the host rocks are very continuous. They're very low energy. They're in a lake. And what you get here is what you're going to get 10 kilometers away. The pyritic part of the stratigraphy is discontinuous, but at a very large scale. So at the scale of, you know, maybe tens of kilometers. But the base metal sulfides are, even the most continuous ones are relatively discontinuous. So the sphalerite is mostly layered, but discontinuous. And then when you look at the galena, it's partially in layers that are discontinuous and partially in sort of blobs in this breccia. And then when you look at the chalcopyrite, which is in these orange, it's concentrated in amongst, you can see there's carbonate all through here, as well as chalcopyrite in cross-cutting zones in these veins in through here, and in through here as well. So it's telling you that there's that in this sample at least, most of, or you know, the zinc was present probably prior to folding, but it certainly wasn't bedded, and that a lot of the galena and chalcopyrite actually deposited during the folding of these layers. So let's look in a bit more detail. And so what we've done is scanned, you know, a few more elements in a bit more detail of this zone in through here. And I'm going to start actually by looking at titanium. And titanium is an interesting one, of course, because geochemists amongst you will probably tell you that titanium doesn't really like to travel very well in hydrothermal fluids, certainly not the relatively low temperature ones that are likely to form mineralization in this area. And we can see that there's a banding relative, showing changing proportions of titanium in here. In fact, there's a spotting in here that, and I haven't looked at it, but some of that is probably representative of detrital titanium. And the interesting thing is when you look at the pyrite, so what I've done is just clipped and shown a little bit of the pyrite distribution, just cropped it so you can follow the same layer and then see where the pyrite is. And there's first thing to say is that a lot of the pyrite layering is coming into what look like detrital layers. It's not so anybody who says that this pyrite rained down from the sea floor will have to explain where all the titanium came from. But the most pyrite-rich layers are the most titanium poor, which is kind of an interesting observation. And in the interest of time, I won't go through a lot more of the genetic significance of that. But what I will come back to is just look at the distribution of sulfides, just to summarize the sort of timing that we're seeing here. So we've got the bedded sequence of the Urquhart Shale with probably what looks like layer parallel replacement of fine-grained pyrite, which is partially in these very rich layers, but also partially in layers that clearly seems to be replacing pre-existing detrital material. Associated with the folds, we're getting these quartz carbonate veins with a lot of chalcopyrite associated with them that seems to be pulling apart layers that appear to have had pre-existing sphalerite replacement. So the sphalerite itself is also layer controlled replacement. And then at later stages, but still spatially associated with that, with one limb of that fold, we're seeing these galena-rich veins that are also carbonate that are then cut by these more carbonate-rich veins, and the carbonate is anchorite, and that later generation of veins has got a lot more chalcopyrite in the orange here, and sphalerite in the green. So that's my rock. I love it. That's enough for me. I think I've run over time a bit, so I'm going to pass straight on to Peter. If I can. Oops, I'm using the wrong mouse.
Right, thanks for that. All right. So yeah, my PhD project's at Dugald River. So I'm at JCU and my sponsorship through MMG. So I've tried to put everything in the bottom left corner for the Zoom window. But for those of you who don't know where Dugald River is, it's in the Eastern Fold Belt, roughly 65 kilometers northwest of Cloncurry. It's a fairly new mine, having started commercial production in 2017, and it's expected 25-year life of mine. So I'll be talking about sigmoidal lenses, not really a rock, but more a feature. On face value, they're quite bland, especially compared to Rick's rock, especially the color one. So what's interesting is more in what they represent and the information that you can extract. So because my project's looking at the structural paragenesis of the mine and mainly building a 3D model, just measuring the orientation of the structures isn't enough. You need to start looking at what are the kinematics and can you extract as much information as possible in this limited space in terms of the underground drives. So these lenses are picked up in pretty much any part of the mine, and they're quite restricted in where you find them in the shear zone. So mostly they'll be in these very high graphitic parts of the shear compared to the surrounding rock. And they typically show strike slip as well as down dip lineations, which is not surprising given the low friction surfaces that they have. So one of the main features that you have is the asymmetry that's brought up by it. So if you look at the sigmoidal curve, it shows that you have this right lateral dextral sense of shear. and at Dugald River, that's top to the northeast. So going beyond that, when you start breaking open these lenses, you'll find that you have the sulfide accumulation, and the sulfides are parallel to the sigmoidal curve, which kind of gives you this relative timing of post-mineralization for the development of these sigmoidal lenses. So what you can find is the synthetic drag, and where these different little shears link up, you can start finding that they form these discrete shears in this essentially anastomosing pattern. So this tends to occur on various scales. So it brings us to the next point, which is the fractal geometry that these lenses show. So when you're looking at the drive, it's very difficult to see them. Unfortunately, this image here is actually from a subvertical shear. So these ones typically show, both strike slip and down dip delineations in the same drive, as well as localized reversal of the expected sensitive shear from dextral top northeast to the sinistral top to the northwest. So, sorry. I drew some of the more prominent lenses, and what you can do then is start looking at a smaller and smaller version of these. So using that yellow box, we can go to the left image there, which has a smaller sigmoidal lens and a smaller one, and again a smaller one. So normally when you pick up these lenses, they'll start falling apart, and the smaller fragments have the same geometry as the larger ones. So what information can you extract from this? So while you can stand there and measure the planes and take notes of the geometry, you have to start thinking about how can I extrapolate this out towards the larger scale. So for instance, with my modeling, I've started figuring out that this geometry is actually replicated by the larger structures. So you have these curvy planar strike extensive shears that are interlinked by subordinate structures. So that starts that makes you start thinking, is like, if these structures are related to sigmoidal lenses, can you use the sigmoidal lenses to find clues of the geometry and the distribution of the ore, in the sense that, given that the sigmoidal lens is most likely post-date mineralization, therefore the shears might offset or change the geometry of your expected ore. So I think that's pretty much my story. Spoke a little bit fast there compared to Rick, but I think I'll pass it on to who's next, Paul.
Yeah, thanks. Thanks, Peter. Right. Share my screen here. Oh. There we go. I'll bring up my couple of diagrams. Oh. There we go. I hope you can all see that. Yeah, look, I wanted to talk about Ernest Henry and show a few rocks, and in particular, I wanted to have a bit of a look at how the textures and I guess the mineralogy change as you come into the high grade zones at Ernest Henry. And it reminded me of when I was working out around Ernest Henry, probably about 15 or 20 years ago now, and we're doing some brownfields exploration. And there was a hole went down about 80 metres, I think it was, along strike from Ernest Henry. And we were all a bit gobsmacked when you sit down and you actually look at, for example, the base metal assays. And I remember the question being asked, well, if you drilled this in a hole out in the middle of nowhere, how would you know that you were near a 100+ million tonne deposit, and would you know which way to go? And since then, there's been a lot more work at Ernest Henry by both Xstrata, Glencore geologists and the DNRME and others understanding that geology and the alteration in particular. So I wanted to show a couple of diagrams, but a couple of rocks, but just to put them into texture, into context. This is the drill hole they're from. This grey shape here is a very quick and dirty, about 0.5% copper isosurface through the deposit. So this hole we're going to look at is entirely in the deposit. What you'll see on the drill hole in blue is the FV2 unit, which is the ore breccia, And you can see the grade within that. This is copper grade plotted on the right here in red. Basically, just over 2% is the maximum copper on that. And you can see there's essentially 1, 2, 3 sort of high-grade lenses within the ore deposit. So I've grabbed a couple of pieces of drill core photos, and what we're looking at is this ramp up here as we go into higher grade. So the first sample will be from the lower grade, and the second, and then the third once we get into that higher grade zone. Okay, I should have put all my numbers on the left, I'm afraid. Most people have their pictures here on the right. So you can see these 3 pieces of core, which were taken from some of the work of Natalie Benici, who did a PhD out in this neck of the woods. And what I wanted to show is over an interval of about 30 metres. Okay, so this is 147 metres downhole here to 178, so 30 metres. The change in the textures and the mineralogy as we go in towards the higher grade. Okay, so you can see the grade. These are 2 metre interval assays over here. So we're sort of heading up from 0.6 copper, 1.15, and to over 2% copper. So the first thing I guess is the host rock here is part of the Mount Fort Constantine volcanics. I think they're about 1730 million years is the age of those. They're felsic to intermediate rocks in the Ernest Henry area. But you can see that these red clasts over here on the left and this more coherent rock over here on the right. So those red clasts are the Mount Fort Constantine volcanics that have undergone a lot of K feldspar alteration, which is pretty intense in the immediate ore environs. So that what you'll see here is I should note also in terms of the host rock, in this second picture, you can see these big quartz blebs or blobs. I think they're probably amadules from vesicles in maybe some more mafic part of the volcanic sequence. But so to get back to the texture, so this unit out here on the right hand end of this drill core, you can see it's more coherent than that. There is a breccia over here, but this is more typical as you're on the flanks of the high grade, and I guess it's been called crackle, crackle breccia or a bird's wing texture. And this white material is the carbonate in the rock. Okay, and with that carbonate, you might get some fine grained magnetite and biotite, for example, when you're out away from the high grades. Then as you step closer in towards the higher grade, you will start to see here that the rock is obviously starting to be brecciated a bit more, and it's not quite as coherent as above. And then as you go further into the high grade, you'll see that whilst there might be some large clasts here, typically it's much the clasts are finer grained, and you start to move into a matrix supported breccia. And that matrix, it's a bit hard to tell. It's all dark, I guess, but there's a lot of magnetite here and a lot of pyrite and chalcopyrite. There are little bits of carbonate, and there's also a bit of quartz in there. But the key point being that you've gone to finer grain, matrix supported, and as you actually, whilst these carbonate crackle breccias are an indication that you're getting close to grade, as you get into the higher grade, for example, in this example, you then start to lose the carbonate again, and you're getting more magnetite and sulfides in there. So the texture provides a nice indicator of which way you're moving, so that hopefully that texture is a vector to tell you, which way you should continue your drilling. So that's the texture. The other interesting part I wanted to show was the mineralogy. So if you look at this at this top piece of drill core, higher up in the hole, you do have some carbonate there, and you do have some in the next hole, and then as you get down to the bottom, that carbonate is disappearing. But what you're also seeing, and it's what you'd expect, is that your sulfide content is starting to pick up as well. So that whilst in this type of rock, there's very little sulfides, you might get little bits of it. There's some over here in this more brecciated part, But as you go close to the high grade, as you'd expect, your sulfide content really seems to pick up. So these are some rocks. These are some of my favourites. I should I won't talk anything more about them there, but I should say that you know, the Ernest Henry deposit has been through a lot of study, and in particular in the last few years, the DNRME has been doing a lot of work there, a lot of high logging work as well. So that sort of data is available if people want to look at it. And I should also note as well that there is now starting to be a great drill core collection in the DNRME facility in Mount Isa, including a lot of Ernest Henry holes. So that if you're passing that way, you should organise beforehand, and you can have a bit of a look at this sort of stuff at your own leisure and up close and personal. So I'll leave it there and stop my sharing for whoever's going on next.
Yeah, thank you. And I will come with my story about the tick hill at the moment. Yes, sharing my screen. Yes. So for the 50 samples from the tick hill, this is my PhD project in JCUs. So generally, the tick hill is located in the southern part of the Mary Kathleen domain. And this is our map of the tick hill. I just have a quick note about the ore mineralization zone.
Sorry, Tron, can I just interrupt there? If you go to display settings, click on display settings and change to your other screen, because we're seeing the presenter's view.
Oh, I'm sorry.
If you go top left. Up top left there, where it says display settings.
Screen. Yeah.
No, where it says display, I'm pointing, it's no point to do that. If you go to the presenter view screen and choose display settings, then because what we're seeing is the presenter's view. We're seeing your slide and the next slide. No, you don't have to stop sharing. Yeah.
Yeah, I share again.
Yeah, okay.
So, yeah. And share my screen too and share it. Now, is that okay? Now?
Perfect.
Yeah, thank you very much. So for the generally about the tick hill gold mine, so in the peak map, we have the ore mineralization in the center of the peak, and it's hosted in the biotite-rich schist and bounded by the foot-worn bauxite and hanging-worn bauxite. And further is the can silicate integrated with the amphibonite. So coming to the favorite samples, most of people are interested and impressed about the galastone in the tick hill, which is very gold rich. And actually it is the quartz feldspar myonite. And if we have the close look, for example, I zoom in about 2 centimeters here, we can see that the gold very clearly. And the gold normally is just, commonly is just located in the space between the quartz grain. And the point is the gold sitting there is normally gold only, without the other sulfide minerals. And the gold is only in the quartz, not in the feldspar. And if we have close look, we can see some minor vein cutting across the monolithic fabric. And this sample is not perfect sample to show the this is, we call that east-west vein, micro vein. But next slide we will see more samples with that. So this is the typical gold-rich samples of the tick hill, but this is mostly in the shallow levels. In the deeper levels, we have different type of gold-rich samples. So in the first line, we have the major quartz feldspar magnetite, which is the major gold-hosted unit. What about the other gold-hosted unit? So gold-hosted units at the depth commonly is the intense silicified unit like this, or it occurs in the biotite-rich schist, and normally it occurs in association with the microveins, the sheeted vein as you see here, the microvein here, or the brachiation, which is caused by the intense of the sheeted veins. Or also in the other sample, we also have the gold in the lower part of the hanging worm quartzite. So the sample, this sample will show you the relationship between the brachiation caused by the intense east-west sheeted veins and the gold mineralization. In the gold-rich or gold-rich zone, for example, in 2 drill holes here, the sheeted veins are very clear, and you can see the sheeted vein cause the fracture of the core. It's normally the east-west sheeted vein will go along with the core axis, parallel to the core axis. Also in this one, you will see very fractured core, which is caused by the intense sheeted veins. And this is normally over 15 grams per ton. In the other cross section, we will see some drill holes with the richest gold in that drill holes is just less than 1 ppm. And for example, in this drill holes, we can see just a few sheeted veins along the core. And the spatial relationship between sheeted veins and gold was observed in every drill holes. Everywhere we have the intense sheeted veins, we will have the gold-rich ore zone. The brachiation and the sheeted veins sometimes occur in the very gold-rich zone, but also occur at the bottom of the gold-rich zone. For example, in this drill holes, you can see the brachiation caused by the intense sheeted vein and some brachiation texture here. This is the very gold-rich unit, and you can see the gold is more than 80 grams per ton, just about 3 to 5 meters above the brachiation and the intense sheeted vein zone. So about the alteration, this sample will show you some alteration neurologies. For example, this is very gold-rich portion in the intense silicified zone, and the gold occur with the feldspar and quartz feldspar metasomatism and alteration. It also occur inside the chloride and epidote, and you can see the other alteration neurons is about hematite. So clearly in this sample we have the hematite, quartz and feldspar, and we have chloride and epidote. So the red pegmatite is also very interested samples in Tick Hill. So in Tick Hill we have picked up a few pegmatite samples. One of them is from the north peak one of the Tick Hill. That is parallel to the D3 shear zones that form the mineralization in the center of the peak. And this is the close look of the pegmatite, the late pegmatite. The late pegmatite associated with the anichelon quartz vein. And we have dated that pegmatite, and it gave very good age of 1522 years old, million years old, with number of concordant analysis is 80, about 80. And for the geochem samples, the geochem data of the same samples, we have 0.7 ppb of gold. So based on this, and also from the mapping in thick hill and also the core loxy and the other data, we think that the gold mineralization related to this stage, this phase of the pegmatite. And that's my story about the thick hill. Thank you. I will come with the next person. Yeah, Matt, please.
Right, share screen.
You're on.
Yeah. Actually, one sec, guys. Sorry about that. Alrighty, let's get started. So yeah, I'd like to thank Rick firstly for inviting me to do this, and having said that, I feel a little bit like an imposter compared to the experience of the other speakers today, but nonetheless, I'll push on and present my favourite rock from northwest Queensland. It's from the Cannington deposit, and if I say anything that infuriates anyone, I'll plead inexperience, so never mind. All right, let's go. I had the privilege to work at Cannington for a few years until about 2015, and I've continued to associate with the deposit and the geos as much as possible since then. It's a broken hill type deposit. It's exceptionally high silver grades and some really interesting petrogenetic history there. And there's a lot to love about the deposit, from like the really high grade specky ore that typifies the main mined areas of Cannington throughout to the peripherals where there's silicified altered zones, which are also very, very beautiful. But having to pick a favourite, I've gone with the lowest grade ore lithology. It's called Inveravon, and I've even brought my favourite bit, and you can't really see it because of the background, but there it is there. It's my favourite rock. I took it quite literally like Rick did, and so that's with me today for good luck. So let's get started. Inveravon, like all Cannington lithologies, is named after a cattle station near the mine. As I said before, it's the lowest grade of the ore types, and it's quite zinc rich compared to many of the other ore types. So you can see here a schematic sort of map section from the Cannington deposit, just to give you some context as to where Inveravon lies to the other ore deposits. So what we have here is a northern and southern zone for the Cannington deposit, truncated by the and slightly offset by the Trapel Fault. In the north and south, you can see this green core amphibolite body. Around this body, you see a lot of quartzites that host the majority of the high-grade ore in the north and the south. And here, particularly, you can see in the northern zone this purple lithology, and that's actually the Inveravon there, sitting a little bit further outboard of the main lithological groups. There is some in the southern zone as well, but we'll just stick to the north zone. So if I take a slightly closer look, this is an east-west cut of the north zone, cross-section from Walters 2002. The previous map section was from the Bowden thesis. And if you want to take a better look at a lot of these types of cross-sections to get a really good understanding of the lithology, you should take a look at the deposit atlas for that. We've heard a lot of information about the compilation of those from Rick's team the past couple of weeks, so I suggest you take a look. So with this one, you can see the core amphibolite body here in the sort of centre, right up against the Trapel Fault, and then surrounding that are the high grade ore zones, which is the Broadlands and the Burnham. In contrast, you can see the Inveravon out on the edges of the deposit, amongst the silicified sort of alteration halo, which comprises schists and lenses of amphibolite and pegmatite and barren quartzites and things like that. So in the top corner, you can see a piece of core provided for me by Lucy Jones at Cannington. This is a piece of Inveravon. It's finely laminated, and this is in contrast to the sort of coarse nuggety ore that I'll show you in a minute from the centre of the ore. It's often got lower temperature gangue mineralogy because it can contain graphite actually. It's usually higher in zinc compared to lead, and it often has a lower silver to lead ratio in the ore. So let's take a look at what it actually looks like. Finally, to see some pictures, which I think was the whole point of this. On the left here, you can see the high grade Cannington ore. So these are examples of these beautiful, very coarse grained galena. I just love this stuff, but we're not focusing on that today. We're focusing on the beautiful Inveravon on this side, which is beautiful and laminar. This rock can be quite silicious. It's garnet bearing, but it can also have amphibole biotite, chlorite later, and my favourites, of course, are the sulfides, which you can see if you look closely there. I've got a little inset of a polished section, so you can see sphalerite, garnet, galena all together with quartz in one of these bands. This is beautifully. It's a beautifully laminated rock. So thanks to Sarah again and Lucy Jones from Cannington for providing the high grade stuff. And this is my pet rock on my desk here, this photo on the right. So I was lucky enough to get my hands on this stunning image of a piece of Inveravon. I'd like to thank Sam Spinks for that one. This is a micro XRF element map, similar to what Rick showed you, potentially slightly higher resolution, I'm not quite sure, but instead of showing the elements that he had, we've got iron in red, calcium in blue, and zinc in green. And so you can see these beautiful mineralized beds or laminations in the rock. I bet that some of those more speckly bits of red would be garnets. And you can see a lot more of this stuff if you tune in next week, because Jim Austin will be giving us a chat as a part of the series that Helen was talking about earlier. So why I think Inveravon is so cool, well, it's a handsome rock, but from a scientific perspective, it appears to be a lower temperature assemblage. It's been proposed as a precursor or proto-ore to the Cannington deposit, so something that existed prior to the peak metamorphic conditions that typify the Cannington area, which is the southeast of the Mount Isa Inlier. And so what I find fascinating about this is you take something that potentially has primary laminations in it and you expose it to upper amphibolite facies metamorphism, significant deformation, and potentially multiple episodes of metasomatism, at least one, and somehow you've preserved this texture potentially. So that's why I find this rock completely fascinating. So in that vein, I'm going to finish on something that will probably be sort of seen as heresy by some of you, but I find it quite fascinating, and it's just a bit of fun, so why not? So if I make you think about what happens if you take my pet rock that's supposed to be a proto-ore to the Cannington ore deposit, and then you expose it to the pressure and temperature conditions of peak Cannington metamorphism, which is estimated about 650 degrees and 5 kilobar. Well, particularly what happens to the sulfides, and what you find is that the sulfides actually melt. And so on the left here, sorry Rick, I've put some photomicrographs in, but I'll keep it short. On the left here, you've got a photomicrograph of Inveravon, that piece of rock I showed you earlier. It's not heated, and you see these sphalerite and chalcopyrite sort of grains within the rock. But on the right-hand side, you see photomicrographs of a chunk of that same piece of rock that's been heated to those peak metamorphic conditions. And anyone who's experienced sulfide melting textures before will recognise these immediately. These rocks were partially molten when I quenched them. You can see here that there's segregation of the high temperature sulfides from these lower temperature assemblages. And although I haven't measured these for chemistry, these look very similar to the Freeburgite silver bearing sulfur salt assemblages you see in the Cannington deposit proper. So if you take a low % partial melt of silver, lead, zinc and or copper, these things can form at lower amphibolite grade. That's what the literature says. And they produce silver and antimony rich melts. And if you think about this as one of many processes in the genesis of a metamorphosed ore deposit, this may help explain the differences in silver grade that you see between Broken Hill and Cannington. Broken Hill was exposed to higher metamorphic temperatures, and therefore the sulfides may be melted more completely. Whereas Cannington would have experienced only a small amount of partial melting of their sulfides, and that may have acted as a mechanism to concentrate silver in parts of the mine. But you don't have to take my word for it. You can read up. There's some work on it in the literature. I recommend you have a quick look at Tompkins et al. 2007. On that note, I'll finish up, but I'll just leave you with one more photomicrograph. It's the same heated experiment, and this is galena that's migrated through the rock between silicate grain boundaries during the experiment, which was I think it was about a 12-hour experiment. So I think that's fascinating, so I thought I'd show it to you all. Thanks very much.
Okay, can everyone see some favourite rocks from Mount Isa? Is that?
Sure can.
Excellent. Oh, well, thanks Rick and everyone for organising this great webinar. It's great to see so many rocks. It's taken me a disproportionate amount of time to pick some of my favourite rocks from Mount Isa, because I think just about every rock I pick up there over the last 13 years or so has been a favourite rock. There are a few places on the planet which have had so much study. In fact, that's probably one of the reasons why Mount Isa gets discussed so much, is how difficult it has to come to some consensus on the origin. But I was going to kind of try and avoid that today and just look at some of these gorgeous rocks. Let me just unpin that video. So these are, I should mention my co-author, Brad Cave. He's doing a PhD on Mount Isa at the moment and coming up with some fantastic data, which we again won't quite get into. But really, Mount Isa is a zone deposit. When you're down near the Peru fault, basement contact, you have a copper-rich ore system within the silica dolomite halo, and as you move away from that towards the current land surface, you go through a transition zone, and then you go into the more lead zinc rich areas. Now the copper zone towards the base is very much sort of breccia hosted, and as you progress away into the more lead zinc rich zones, it becomes much more layer orientated, sort of following the layers of the Urquhart shale. And really, this little map I'll have in the corner as we go through. So we're going to first start here looking at sort of zone A, we'll call it, and then through the transition zone B and up into those other zones like that. And I guess actually, just before I move on, it is quite interesting how in the past a lot of studies have either been sort of top down, studying the lead zinc, or they've been sort of bottom up, studying the copper. There's been very few studies actually at that interface where the copper and the lead zinc meet, and that's been the main focus on Brad's first couple of years of study. And as Matt very eloquently said, if I do say anything that gets anyone's temperatures up, I'm in Adelaide, so I think I'm a long way from Brisbane. But yeah, it's a great chance to look at some lovely rocks. Here's a good one. This is very typical ore from the silica dolomite zone. This is typically down towards the base of the system, up against the Peru fault there. And here we can see the beautiful, generally just called silica dolomite. Now that in lies, there's actually several stages here. There's an initial carbonate, the dolomite, that's actually busted over by a silica, which isn't necessarily represented in this image. And then there's actually another carbonate associated with the ore, main ore event. In this case, we can see chalcopyrite there, and there's actually a little bit of pyrrhotite there as well. It's actually very easy to see the carbonate too, or the second carbonate. It's the grey material that sort of comes over the top here and crackling up. Now, I should say a caveat to that is when a student called Ben Andrew, who's working at University of Waikato in Mount Isa Mines, when he's looked at these white zones or this carbonate material with cathodoluminescence, it's actually not as easy to pick from just the colour. So there's a whole nother story going on there. But in this lovely image, we have classic Mount Isa chalcopyrite and pyrrhotite. And this little MLA map here is just put in to show that even within the high copper zones, you do get very regularly small inclusions and small crystals of galena and sphalerite within the copper. The chalcopyrite alone within the copper zone of Mount Isa can go up to 600 ppm silver. So that's fairly unusual. The silver's in the chalcopyrite is solid solution, so you don't see it. Most of the silver in the Mount Isa deposit obviously is associated with either argilliferous galena or tetrahedrite. There's a few notes here that I won't read, but I figured if people want to look back on this on the video, they can read those. As we move slightly further away from the basement contact, here we can still see some silica dolomite, which has busted through some Urquhart shale. The Urquhart shale, so the host rock, is around 1650, plus or minus a little bit. As Rick said earlier, I think everyone's pretty happy. It's lake. It's you know, it's a sort of got quite a lot of primary carbonate in. I chose this image because it has some fine grained pyrite here along the beds that you can see are quite clearly broken by the silica dolomite, and the copper is both discordant and concordant with that. You do get quite a lot of replacement of fine grained pyrite by the chalcopyrite and sphalerite. But I wanted to point out here as well, you've got a few little clasts here of fine grained pyrite bearing Urquhart shale, which is quite common. But what no one's ever found is a clast containing banded lead zinc within that breccia zone. So I think that's quite relevant from a textual point of view. Stepping further away, we get into this transition zone. And I think what we can see here quite clearly, I like Rick's term earlier, polyclinal disharmonic folds. I'm going to use that one as often as I can in the next few weeks. You can see these very, you know, these to me, when I first saw them, I had no idea how you could generate such things in a sort of constrained zone where you have continuous layering either side of it. I kind of look at them myself personally as kind of quite often quite slumpy. I've seen some images of lovely slump rocks textures from lacustrine environments, and these look no different really, but that's personal opinion. But what we can see here is we can see quite a lot of sphalerite and galena taking up sort of obviously the space in between. But as Rick pointed out, there are these discontinuous zones of replacement of sphalerite in these sort of, I guess, essentially more carbonaceous zones. So you can see here, if we follow this zone round, it's quite strong, backs off a bit, and then sort of just peters out as we go through here. And of course, worth mentioning is in all these transition zones, there is quite a lot of coeval chalcopyrite existing with the sphalerite and galena. Galena often taking up relatively late paragenetic timings, as in it was probably liquid for a little bit longer, or you know, within the hydrothermal fluid for a little bit longer. So it does quite often fill up those little cracks right at the end. That's very typical. Another little map here from Brad showing, here's some, this is an MLA map showing clasts of shale with chalcopyrite, sphalerite and galena around the shale. So significantly in some areas, you don't necessarily have sphalerite in the shale. So the replacement is quite selective, which is definitely relevant. As you move away from the transition zone, which we have here on the left, another image from Brad, showing where the sphalerite and galena are both replacing silica dolomite where they can. So there's definitely a post-silica dolomite timing for that sphalerite and galena as well as the copper. As you step away, it becomes more layer controlled. Sphalerite loves replacing carbonate, so you'll quite often see sphalerite, you know, following these beds along, sometimes popping up through a vein and finding another zone. And depending on where you are in the system, you'll have quite galena-rich zones as well. Galena, to my experience, is normally in a breccia kind of environment. It's not so much replacive as sphalerite. And this is all rather typical of moving away from the copper breccia zones. This is one of my favorite rocks. You can actually see this sort of feature quite often in the Mount Isa deposit. It's essentially selective replacement. But having been taught when I started at uni and when I first got to Mount Isa that, you know, the sphalerite and the galena, you know, rained out of the sea and formed all these layers, you actually look at this and you say, particularly here in this sort of zone, how on earth do you do that with a sphalerite rain? And I think it's fair to say there's zero evidence of exhalation in any of the Mount Isa and George Fisher deposits, but there's plenty of evidence of sort of irregular layer replacement. I've just added a couple of lines on just in case you can't see those, but these sort of discontinuities, aquatards, whatever you want to call them, were clearly there before the ore has come in and selectively replaced. Now that's something Bill Perkins noticed back in the day, back in the 70s and 80s. And these are fantastic. These zones are actually, in this particular rock, that's full of very small amount of silica dolomite, as well as some fairly coarse galena sphalerite that's obviously preferred to replace the coarser carbonate in that vein, as opposed to replacing the fine grained carbonate in there. And of course down here we can still see quite a bit of sphalerite overprinting the fine grained pyrite and pre-ore kind of coarsish grained pyrite. It's a whole other story. Thought I'd just chuck in a bit of a nod to Bill Perkins, because he's pointed out these features for years. Just for arrow's sake, there's an arrow, and you can see the sphalerite, which is the orange color, replacing dolomite layers. But in this particular layer, it's found a layer of carbonaceous shale it likes, and it's ducked in there until it's got to one of these discontinuities, and right, can't go any further, we'll just stop there. And you see this on every scale in Mount Isa, from sort of like certainly from the microscope up to you know, huge exposures underground of this sort of thing. So that's one of my favorite rocks for sure. It really does blast out the question of, you know, how did this get here? And then I just thought I'd put in something a little bit different, and looks a little bit like one of Matt's rocks actually, with this rather sort of orangey sphalerite and galena. But the purpose I put these in for is this magnetite. These sort of blobby, weird textures, the grains, all these dark areas, that's all magnetite, coarse-grained hydrothermal magnetite, which I don't believe forms on the bottom of a lake. And you also have this white material, which is Celsian feldspar. Celsian's a barium-rich feldspar. And of course, in Mount Isa, we also have plenty of potassium feldspar as well. Now, it's very worthy of note that the magnetite is cut and broken by all the ore sulfides. So the magnetite and the Celsian were there before the ore. So I think that's quite relevant, and probably something that doesn't get talked about a great deal. These particular rocks, and I'll just pull up another one in a moment, is that these are right down here in the bottom left-hand corner. Here's the map, and these are actually just sitting just off to the side of the very high-grade 3500 ore body. So these are sort of not up along stratigraphy. These are actually just sitting next to it. I wouldn't call them a halo, but there are, you know, there is a fair bit of magnetite. And Brad did ask me to mention, he said, it's always interesting to mention that pre-mineralization alteration is not covered or explained well in these systems that are widely described as SEDEX. So I think with all these things, it's always very healthy to question the model if what you're seeing doesn't fit the model, as Matt was saying just now as well. And it's also worth mentioning that the pre-ore alteration mineralogy at Mount Isa and George Fisher and Hilton includes magnetite, Celsian, potassium feldspar, biotite, apatite, rutile, and monazite. And I thought it was interesting when Rick mentioned earlier that there's quite a lot of titanium, and in every thin section I've looked at from Mount Isa and George Fisher, there is quite a lot of rutile, and I don't think it's all detrital. There's quite a lot of very clear crystal shapes in there, so it's not necessarily detrital crystals, but anyway, the presence of that is very interesting. Here's just one last image of magnetite being taken out by the sphalerite and galena on the edge of some fine-grained pyrite, which is, the fine-grained pyrite predates the magnetite. So there we are. And I think I'll say thank you to that. And anyone who's interested, there are some professional development workshops that we plan to run through the Nexus course at some point this year when things calm down. So I shall stop my share there and hand over to whoever's going to pick up.
Yeah, we haven't actually, no, my video's back on. Yeah. We haven't actually talked about who's going to pick up. Helen, do you want to, or shall I? Thanks, everyone. We didn't mention.
Go for it, Rick.
We didn't mention at the start that there's a Q&A tab. Anybody who has a question for anyone. We pretty much used up our hour, I have to say, but I was filled with dread that we would have been, you know, only 3/4 of the way through by the end of an hour. So I think we did pretty well, given that we got through a lot of rocks in that time. But if there are any questions for anyone, you know, I think we've got time to take a few. There is a virtual drink session that runs up until 5. So, you know, feel free to you know, get stuck in. Don't wait until we call drinks. I see that there's something there. How good is our timing, says Matt? Yes, indeed. Yeah, it was perfect. We've got
Well, here's a question. Ian Gar said, I wasn't aware of the magnetite in the Urquhart Shale. Is this related to demagnetization of the EC
That's an interesting question, actually. No, I don't think it's related. The ECVs have had, you know, a fair amount of hydrothermal fluid through them in various places, and they've definitely got zones where they're less magnetic. I guess the old story or the traditional view is that the ECVs are very much a potential metal source for the Mount Isa deposit. And some work Brad did recently looking at magnetite chemistry is actually very interesting, that people have always said the magnetite could be the source of the copper in Mount Isa, because the ECVs are quite rich in copper, and that is actually held within the magnetite. But the magnetites in the ECVs actually are really quite enriched in lead and zinc as well. And the conditions you need to leach copper from magnetite are the same as that you would need to leach lead and zinc. So there's no reason why the Urquharts couldn't be the source of the metal for the system. But the magnetite itself, it's a very, we think it's probably a bit earlier than the ore system itself, but Brad has got some data on those, and we will hopefully be putting some work into it. It's a very good question. It's definitely something that we're thinking about as to how that magnetite fits into the story.
And I'll just add to that, those magnetite Celsian zones occur at George Fisher as well, and there's no ECVs in sight. It's a long way from the. They have an ore body called 4-pod that's just absolutely stuffed full of Celsian and magnetite.
I've just changed my background, Rick, to that very zone.
All right, yeah.
That's George Fisher behind me there, and all those.
Oh yeah, well,
no. Like a weatherman. So like the little black dots.
It's a competition.
Yeah.
Does anybody else have any more questions while we have all the panelists here? You can ask about any of the deposits we've heard about today.
Well, I've got a question for Matt, if no one else is going to chuck one in. I was going to say, Matt, you know, what if Cannington wasn't a Broken Hill type? What if it was a scar?
I'm actually more okay with that than I've ever been. I was trying to find the photos, Richard, because I've been working on the silicates there, and I've seen a lot of garnets that have sulfides included, and things that very much look like coexisting phases. And then I've seen this beautiful rock where you've got galena that looks like it's replaced bits of the rock with chloratized garnets. And so I'm seeing these very conflicting very conflicting textures that talk to very different timing for the mineralization. What's more, what differentiates it from Broken Hill is that Cannington is encased in this beautiful, very clear silicate. It's like got this quartz overprint on it that just looks like it's been set in it like some sort of display. So there's obviously something else going on. So I think that there's textures that would be replacements similar to skarn. I'm totally okay with that, but I don't think that I don't think that all of the ore has been brought in post metamorphism. I think you can see the effects of metamorphism on the ore, and so it's a bit of a cop out. But I basically set up with this idea that it was a pre-existing sulfide, base metal sulfide of some sort that's been upgraded through peak metamorphism, and now I think that's part of it, and then there's been some later processes that's mobilized the ore again. So I don't think it's a full-blown skarn, but I certainly think there's a lot of alteration that's not considered in the peak metamorphic models. If that doesn't sound like too much of a cop-out, Richard.
Not at all. Not at all.
Okay.
Very, very, very diplomatic.
Okay.
Talk about covering all bases, Matt.
I had a question for Trong. I remember looking, this is a long time ago, looking at samples from Tick Hill where there seemed to be an association between the hematite and I think titanite associated with it as well, and the gold mineralization, but I wasn't sure from the rocks. You showed rocks that had lots of hematite alteration associated with it, but then you seem to say that, oh no, it's the quartz feldspar and the chloride epidote, but not so much the hematite. So is there but yet the age is very much a kind of you know, not far off the kind of Williams granite suite of mineralization, which is kind of what I was hoping you guys would come up with. So is there a spatial association with the hematite and the gold mineralization?
For the spatial hematite and gold mineralization, it's very clear, and it's very close in all of the samples that I observed. And under microscope, the hematite always occur in the gold mineralization, and even in some grain of gold, which is very close to the magnetite, it's normally or almostly converted to the hematite. And the point is, this is the regional hematite alteration or the local hematite alteration. It is not always easy to identify this is local hematite, which is associated with the gold, or the regional red rock alteration. Yeah, but from all the samples, it's always have close relationship.
Mm-hmm. Good.
Thank you.
Question for me. Do you see any Cuprian sphalerite, copper-bearing sphalerite, call it what you like, in any of the ore zones? Oh, no, for Richard. It's not for me. It's for Richard. I keep forgetting there's two Richards. So it's for you, Richard. Do you see any Cuprian sphalerite, copper-bearing sphalerite, call it what you like, in any of the ore zones at ISA?
I've not actually heard the term Cuprian sphalerite before. If I'm being ignorant, please excuse me. We've been doing a fair bit of work on the trace elements that sphalerite can absorb or take in, and actually that's some work Brad's doing right now. And sphalerite in different conditions will suck in or partition certain elements in it, germanium, gallium, things like that. So we can actually pick the sphalerites quite effectively by their chemistry to some extent. But in terms of Cuprian sphalerite, no, but sphalerite is a very common inclusion within the chalcopyrite in that sense. But I don't think sphalerite likes copper. Please, someone else answer if they know. I think. Well,
it depends, Sam, whether you mean like chalcopyrite disease in the sphalerite, or whether you mean, you know, actual copper bearing sphalerite. I mean, having said that, I'm not, you know, I'm sure that I'd have to think back, but I'm sure that you do see, certainly at George Fisher anyway, you know, the sort of chalcopyrite disease in the areas where, you know, in the common areas where sphalerite and chalcopyrite coexist at George Fisher. But that's really, you know, most of the lower parts of George Fisher are, at least in the hanging wall, are kind of Richard's transition zone.
We've certainly, and again, of course, the main thing that varies in the sphalerite would be the iron content. So the relatively early sphalerites have got paragenetically slightly, you know, in the sort of extended period, they have a bit more iron, and any sphalerite that has been, I guess, actually I'm not going to use the word, but any sphalerite that sort of ends up in some of the later veins can have lower iron, so they often have sort of that paler orange color. So, but you know, I'll have to pick that up with you another time, Sam, but not specifically.
Shall we move to drinks, and then we can have have more of a flowing discussion?
Sounds good.
Yeah.